So hello everybody, and we continue our webinar series on data visualization. And in this webinar, we are going to talk about projections which could be used for multidimensional data visualization. Again, webinar is prepared by Tomas Krilavicius and Monika Zdanaviciute from Faculty of Informatics at Vytautas Magnus University, Lithuania. So we talked about different types of data, and of course, usually we have multidimensional data, and when simple direct methods are not sufficient, then we get into strange world of projections. So probably here, of course, you can identify or recognize Alice in Wonderland, but actually, in some sense, when we move to projections and multidimensional data, again, we have something strange and while useful, but requires a lot of more knowledge. In general, of course, projections are not so complicated. So let's say that even in simple two-dimensional case, for example, we have line A and we wanted to project to line B. So what we do, we can do very direct projection, and A1 would be direct projection of A on B. So that what it means. But in this case, of course, we are going to look at a higher number of dimensions and more complex data. So for example, in this case, we show what kind of projections, very basic projections you can get when you want to move from 3 dimensions to 2 dimensions. So basically, from 3-dimensional space, you move all the objects to 2 dimensions. And usually that's what we want. So usually if we have number of dimensions higher than 3, we want to project them to 2 or 3-dimensional space to be able to visualize them and to observe them. And it requires already good planning and good understanding of your data. Because in this case, you always lose some information. So basically, you have to choose between data structure, so between relations between different observations and number of dimensions. And of course, by removing dimensions, by projecting data to less dimensions, you lose some information. So basically what you have to do when working on such type of visualization, you have to explore different possibilities. You have to play around with simple visualization, direct multidimensional visualization methods. And as I mentioned before, you have to get some understanding of your data. So here we are going to look a bit at more complex view. So at mathematical structures which usually represent your data. So let's say that we have data which is represented by matrix X or vectors x1, xn, where xi, j are separate values in this matrix. So basically one vector, it could be your one object, and each element of the vector, basically it's different dimension or different feature describing this object. So we have n-dimensional space, and we can have any number. In this case, of course, it's m, but it doesn't matter too much. We have specific number of objects. And what we want to do, we want to move from this n-dimensional space to lower space. And this lower space should be, of course, should have less dimensions. So as I have mentioned before, it should be 2 or 3 dimensions. So basically, instead of having object which is defined by n features, we have to transform this object to object y in this case, which has d dimensions, and d is a lot smaller than n. So, and it means that basically, depending on the method, these features can be different types of combinations of the features, real features we had before. So basically what we try to do usually, we try to minimize number of dimensions while preserving data structure versus our selected criteria. And usually in what we look at distance between vectors or distance between these objects in our higher or lower dimensional space. And of course, it allows us again to identify interesting aspects of data. So clusters, outliers, different patterns, groupings of these objects, based on which we can do something. And we start from the simpler approach for data projection. So it's called principal components analysis, or in short, PCA. So it's linear approach to minimize number of dimensions, and we will explain it using two-dimensional space. So if we look at the top left picture, basically you can see that we have feature 1 and feature 2, and we have scatter plot of these features. And what we want to do, actually, we want to have a different view on, for example, to represent them using only one dimension. So what we do, basically we choose direction where distribution of the values is highest in 2 dimensions, and choose this direction for the first principal component. Then next one will be orthogonal component. So in 2-dimensional space, it's easy. Of course, in higher number of dimensions, we can rotate it around to choose it. And basically projection of these points values from feature 1 and feature 2 to principal component 1 and principal component 2 is actually our projection and way to minimize number of dimensions, as is seen at the bottom of the figure. So again, as I have explained, so basically our central point could be empirical mean along each dimension in this visualization, and the first principal component goes along the line or over the central point, and the highest deviation between points, another one is orthogonal to PC2, etc., etc. So the more dimensions you have, the more rotations you do, basically. So, of course, we have mathematical tools and procedures how to calculate it. So here we show, actually, we use visualizations to explain how visualization works. So basically, sometimes it helps to think about it as, in some sense, rotating axis in such a way that first axis or the main axis points in the along highest deviation between objects. When we choose another highest, and another. So what we do, you kind of rotate the axis around. But of course, you may have some issues with these visualizations. So sometimes, depending on what kind of dimensions and plots you have, it may work, or you can get very bad visualizations, like in this case, where projections, they coincide and you don't see that you have two categories. And of course, you can have another issue. So if you have outliers, so basically on the top right corner of this visualization, basically all other objects, they get into some small space and you cannot distinguish between them. So what you can do, basically, if you can identify outliers in your data, and actually they are pretty easy to identify if you are using, for example, box plots, which are discussed in another visualization, then you can remove this outlier, again apply principal component analysis, look at it. If you see more outliers, repeat the process again. So basically, you can choose objects which you want to analyze and which structure between objects is most interesting for you. And actually, if you would follow the link in the slides, you may find an interactive PCA demo. Again, what's nice, we are talking about visualization, and interactive visualizations, which we mentioned in another webinars, are used to explain how it works. So we leave it for you as independent work, but please play around with it so you get better understanding how it works and what kind of issues you get if you do it in the wrong way. Then we have a whole family of other methods which are more complicated, and they are called multidimensional scaling. Again, what we do basically the same stuff. So we have very high number of dimensions. As it was mentioned before, basically you can use the same matrices to represent them, so vectors and collection of objects in the matrix. And what we do, in this case, we try to preserve specific relations between these objects. So most of the time, this relation is either similarity or dissimilarity. So similarity could be defined, for example, using Euclidean or Manhattan metrics or your defined metrics, which define which objects are more similar, which objects are less similar. And or you can use opposite things. So basically you can define dissimilarity. And similar objects usually should be near to each other in your visualization, by dissimilar far. So basically what you try to do by applying multidimensional scaling, you are trying to project from high number of dimensions to low number of dimensions, but this similarity and dissimilarity between all the particular objects should change only a little bit. So the less it changes, the better projection you get. And basically what you do, so in this example, for example, we have three-dimensional source space, and on the right-hand side, we have target space where we move to two dimensions. And what we do, basically, we want to preserve, for example, in this case, distance between xi and xj. It should be as similar to this yi, yj distance. So basically, delta ij should be as similar to dij as possible. And of course, it allows us to define basically function where we solve optimization problem, where we are trying to choose the best projection, which conforms to our requirements. And I showed some examples actually, which can be used maybe not necessarily to tourism data, but for example, maps. So what we can start actually in this case, quite often we can start not only from points in multidimensional space, but just from distances between these points. And in this case, we have multidimensional visualization of Lithuanian map. So these dots and titles are Lithuanian towns. But what we get actually and what we have in visualizations, so it does not preserve orientation. So what we have to look only at relations between these points and the structure. And for example, in this case, we have Lithuanian map, but it's inverted vertically. So actually, the town on top, Druskininkai, actually is the most southern Lithuanian town. So we have to rotate things. And we should get something like in this figure. And this map, basically, it's restored only from distances between different Lithuanian towns. Of course, it may have some errors. And it raises additional questions. So in this case, of course, we know that our goal is 2 dimensions. But let's imagine that we have distances and we map Lithuania to 3-dimensional map, while distances actually are on 2-dimensional space. So we get something strange and hard to explain. So you have to be very careful, or you move to the world like in Alice in Wonderland, where you get some very strange effects which are hard to explain. And actually, it could be used for very different data. So again, this example actually is from political analysis. So it's visualization of Lithuanian parliamentary voting. And it's So it's, let's say, kind of historical data. So period is from 2008 to 2009. And basically, you get a lot of votes during this period, for example, several thousand votes for each member of parliament. And then, of course, it's very hard to compare them. So what you can do, you can apply a multidimensional scaling to project them to 2 dimensions. And in this figure, basically, you get Lithuanian parliament of that period. And you can see it's already, even knowing nothing about the parliament, you can see that on one side you have position, on another opposition. So basically 2 competing sides. Then, of course, different colors represent different factions. And actually, what's even more fun, so we have these gray dots, which is kind of independent parliamentary members, which do not belong neither to any faction, and we are kind of neutral. So again, you can see that we are in the middle. So basically, political scientists can tell a lot about what's happening about it. And of course, such tools can be applied for very different data types, and you can get a lot of interesting insights from them. And here we have the same visualization. So again, these towns you can already, or locations you can already identify. And again, this map is restored from just distances between all these towns. And of course, you can see that again, it's inverted version. So we have Athens at the top, and Stockholm at the bottom. But actually, if we would invert it again, we could get surprisingly good representation of Europe. Of course, it's just restoration. Of course, we don't have exact numbers, but just remember that actually in case of projections, we are trying to change dimensions, and we lose some information. But if you do it properly, you can see that actually the result could be surprisingly nice. So again, these are, let's say, one of the most complicated multidimensional visualization methods. So basically, if you want to apply them, you may require preliminary understanding of both methods and what these charts mean. You may need to understand some mathematical tools, some mathematical methods, like to know how to define distances, similarity or dissimilarity. But then the idea is the same. Basically, the best methods to visualize your data are methods which give the best answer to the question. And again, of course, different methods may work better for different audiences. So of course, when we are talking about multidimensional visualization, these plots may require a lot more explanations. You may need to, to draw a lot of different plots and to choose the best ones to represent your idea. But then, your effort will pay back when you will be able easily to explain your idea, to explain your findings. And as usual, interactive visualizations are very helpful in this case for different analysis. So for example, you can project data to 3 dimensions and then to build interactive tools where you can look at positions of your objects in 3-dimensional space from different angles to zoom in, to zoom out, basically to explore what's happening there. And of course, when it comes to quality of visualization, you have to start with questions. So basically what you want to find in this data, then of course you need data, and you have to ensure quality of your data, because if your data is wrong, if you have errors, if you have missing values, your result is not going to be very useful. And when you have question and data, you have to choose right visualization to answer your question. And when all these 3 things, question, data, and visualization methods, show the same, then you have high quality visualization. So basically, Please use visualizations to explain your results, to explore your data, and good luck in that. Thank you for listening to our webinar.